So parametric equations, a parameter is a variable, and it's usually an additional variable to, if we're in 2 dimensions, x and y, or 3 dimensions, x, y, z. You'll see 3-dimensional stuff if you go into calculus 3 and beyond. What we learned in trigonometry is that if we pick any point here, and any point here has coordinates x, y, where the x and the y have to satisfy that equation, we also know that connecting a radius to that and using the positive x-axis as our reference side for an angle, that there's a connection between x, y, r, and theta. And the connection is that x can be viewed as r times the cosine of that angle. In this case, r is 1, or x is cosine. And we also know that y equals r times the sine of theta. So this relationship between x and y here, and the radius and the angle, we can choose any radius circle we want. That can vary, right? So in this case, r is a parameter for any circle, its radius. And then if we pick any point on the circle and we use the positive x-axis as the reference for an angle, then the angle is going to vary for any particular point we pick. So the angle varies. So given if we stick with our original variables, or x and y, then both r and theta are parameters for x and y. In this case, specifically, the parameters for a point on a circle. And you can have as many parameters as you want, depending on the situation. In this case, I have 2 variables, x, y, and I have 2 parameters, r and theta. If, again, I focus on the unit circle, then I can simplify it down to a single parameter, which is just the angle. And so then I can create x and y based on any angle I want. And I can let that angle change. And as the angle changes, I can trace out a circle. So if I want to view the unit circle as a parametric graph, then I would say theta, standard angle, is my parameter. And in this case, if I let x equal the cosine of theta and y equal the sine of theta, then those are my parametric equations. And first I'll make a table to review way back from like week 1 of our class together of choosing theta and then calculating x and y, picking some of our favorite angles like 0, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. If theta is 0, cosine of 0 is 1. If theta is 0, sine of 0 is 0. All right, so graphically, starting at theta equals 0, I've just plotted that point right there, if that's 1 unit away from the origin. And then at pi over 6, cosine at pi over 6 is the square root of 2. 3 there. And then the y value would have been 1/2. So I'm going to get a point around here-ish. And at pi over 4, oops, got pi over 4 written. cosine of pi over 4 is the square root of 3 over 2 over 2. And the sine is also square root of 2 over 2. So I'm going to get a point that's around here-ish. And at pi over 3, cosine is 1/2. And the sine square root of 3 over 2. That's going to give me a point about here-ish. And then at pi over 2, cosine is 0, sine is 1, and I'm going to get that point there. So using the parameter theta, I can trace the circle in the counterclockwise direction starting here, where theta is 0. And at this point, I'm stopping right here, where theta is pi over 2. So what parametric equations allow us to do is trace a particular curve in a particular direction at a particular speed. We can change the speed the parameter moves as we plot. And we can also change the direction it moves. So I set up a Desmos file that we can do parametrically. So I'm going to whip that out, and we're going to experiment with looking at some parametric equations on paper and then seeing what happens with the graph on a computer. So if you go to week 10, I have a link there to a Desmos file I set up. There we go, Desmos parametric graph. And it's set up for you to type in an f of x for the x parametric equation and a g of x for the y parametric equation. And instead of a theta, I'm using an a for my parameter. And then it will do two things. It'll show you what point A is at currently, and then it will try to trace that out for you. So I'm going to get rid of that one there. Back to that one later. And I want to put in the graph for cosine. And here we have to use x, and then later my other things will replace x with a. And then this one is going to be sine of x. And I'm starting a at 0. At the moment, a is 0.3. And so as I increase the parameter, it's then going to start plotting this out. So there's approximately pi over 2 right there. And we can see that looks like it's plotting out a semicircle or a quarter circle, which it should based on what we know about sine and cosine. So that's the idea of a parametric equation, when we take a different variable and we use it to help trace out a graph. And in this case, we're using x and y as our versions. You could do a parameter in polar and trace out a polar graph based on some other parameter. We're going to stick with rectangular for now. In some future math class, you might play around with polar parameterizations. This is a rectangular parameterization. And we can parameterize anything we want. Now, I mentioned that there's more than one way to parameterize a particular thing, like the unit circle. Like suppose here, instead of plotting this counterclockwise, suppose I wanted to plot this out clockwise. There's several ways to make that happen. Okay, let's do a clockwise unit circle. So let's see, I want to go clockwise. So that's kind of changing, measuring theta, positive being counterclockwise to, we want to go the other way, which would be negative, wouldn't it? So I think to change that, all I have to do is try something like cosine of negative theta. Y is sine of negative theta, because that'll give me the opposite of each angle I start with, which should head in the other direction. All right, so that is, if I consider the same idea, that I'm going to let theta be 0, pi over 6, pi over 4, pi over 3, and so on, and then calculate x and y, I think that'll head me in the other direction if I take the opposite of each of those angles there. So I'm not going to calculate the points individually at the moment. I'm just going to go try this in the Desmos quick drawer I just made to see if that really will work. And every once in a while, I get an idea on how to do a parameterization that doesn't quite do what I want. Let's see if this one does what I want. So I'm just going to jump in here and make that a negative x and a negative x. And then I'm just going to go back to see if it really does trace the way I think it does. Yeah, now it's just doing it in the other direction. Kind of cool. I also mentioned you can speed up or slow down the parameterization. So let's say theta was also seconds. How many seconds would it take me to draw the whole unit circle? What's the value of theta to make a complete revolution? 2 pi. So if theta is also seconds, then it would take 2 pi seconds to draw the whole thing, right? And notice that if I interpret A as seconds, then I'm going to have to go all the way up to 2 pi, which is going to be 6 point something before I see the whole thing. What if instead I wanted to graph this in a little over 3 seconds? I'd want to step through this quicker. Okay, yeah, in like pi seconds. Okay, so usually maybe I wanted to go twice as fast, that I might double the angle and see what happens. So we could just experiment and try it. I'm going to switch back to the other direction by getting rid of the negatives. What happens if I put a 2x instead of just an x? So I'm going to put this over to 0 to see the surprise. And then start tracing. Oh, yeah, now it graphed it quicker. If I'm saying theta is also seconds, it's going to graph it in 3.14 seconds. Right, so my point is for any parameterization, you have some curve in space you want to be able to graph in time, point by point. There are ways to do it with x and y, and you can make it go faster or slower, and you can control the direction of it. Okay? So when we graph parametric equations, we usually want to indicate where the parameter is, at what point is the parameter 0, and then from there, what direction is it tracing? Okay. So just to be clear on that, let's go back to my first example. Here, notice I put an arrow on my graph to indicate I'm starting here at theta equals 0, and then as the parameter increases, that's the direction it's tracing. With the second version, where I replaced theta with negative theta, then this graph would look similar but different. It's still going to start, if that's 1 right there, that's my theta equals 0, but this graph is going to head in that direction as it comes around and plots the unit circle. And so with parametric graphs, we usually indicate at least where the parameter is 0, and then what direction does it go from there. And sometimes we'll also indicate other values, like at this point over here, that's where theta would be equal to pi. All right, let's try another problem. Let's take parametric line. Ooh. Oh, actually, we're going to do a line segment. Could do a whole one. We're just going to say for now. So what I would like to do is take the points 1, 2, and then I want to get over to the point, let's say 5, 5, 4. So I want to go from here to there. Oops, not vectors. You can parameterize vectors too. Just the point to the point 5, 4. And I want to make that happen in once t equals 1 second. So t is going to be my parameter here. So how would we make that happen? So again, I'm just going to make a note of my graph. I want this point here to be t equals 0 would be the easiest choice to start with. And then that means this point here would have to happen at t equals 1. I want to connect those things together. To do that, I'm going to start by building a table to think about this, where t is going to be my input, and t is going to help me output an x, and it's going to help me output a y. I know that when t equals 0, I want x to be 1 and y to be 2. And at t equals 1, I want x to be 5 and y to be 4. And to parameterize this line, that's called a parameterization. That means I want to come up with x as a function of t and y as a function of t. But y is probably going to be a different function, so we better call that one g. If I just focus on the t and x for a moment, well, the easiest way to get from t equals 0 to x equals 1 and t equals 1 and y equals 5 would just be to create a line through those points. Right? So I'm kind of going to create a line between a line. So that means for the function x equals f of t, I'm just going to make an m, instead of mx plus b, it's going to be mt plus b. And this one's actually pretty easy to make because I chose the independent variable to have a change of 1. Right? I'm going from 0 to 1. So the slope means I have to get from 1 to 5. How far is that? 4 in 1 second. I have to change x by 4 in 1 second. So my rate of change there is 4 over 1 times t. And what's my starting x value? Plus 1. So it looks like if I do 4t plus 1, that will help me get from x equals 1 to x equals 5 as t goes from 0 to 1. I can do a similar thing if I focus on the y equation here. I want to go from t0, 1 to y 2, 4. So what's the change in y? Just 2. And what's the change in t? Just 1. So it'd be 2 over 1 t would be my rate of change, or 2 over 1 is the rate of change, and then times t. And then what is the starting y value? Oh, the starting one would t equals 0 would be 2. Right, so cleaning that up, I get 2t plus 1. And so my claim is that if you parametrically apply this, you will get exactly that line segment right there. Okay, and we can kind of test it out. Let's see, if t equals 0, and I plug 0 in here, 4 times 0 is 0, plus 1 is 1. So that's going to definitely put me at the x equals 1 here. And then down here, if t is 0.
Isn't it 2t plus 2?
That should be a 2 there. Good job. Thank you. No, you're not crazy. I'm just miswriting things. That's going to give me x equals 2. So at t equals 0, I'm definitely at that point right there. If t equals 1, well, 1 times 4 is 4, plus 1 is 5. So that's good. It's going to put me x equals 5. And then over here, 1 times 2 is 2, plus 2 is 4. All right, so it's definitely going to put me there. Question is, when t is a half, is it really going to put me in the middle there? All right, let's double check t equals a half. Blue. t equals a half. Okay, so I'm gonna write that down. That's gonna give me 4 times a half plus 1 for x, which is 2 plus 1 or 3. And y would be 2 times a half plus 2. Half of 2 is 1 plus 2 is 3. Where's 3, 3? 1, 2, 3, 1, 2, 3. Oh shit, that's right in the middle too. It looks like this might work. Let's trace it out in Desmos and see. So again, I think my parameterization here is x equals 4t plus 1, y equals 2t plus 2. And it should, in 1 second from my parameter, or 0 to 1 of my parameter, get me that line segment. All right, so this is now going to be 4x plus 1. Put that at 0. And this is 2x plus 2. So there's my point 1, 2. And as I let my parameter go up to 1, it should trace a straight line and end at the point 5, 4 there. Cool, it worked. Holy cool, holy moly.